All right, just pass it over.
Hey, thank you. So again, my name is Hagen. You heard from me a little bit earlier, but now I want to show you around the AFLOW database and the API that will help you access it and make the most out of it. So this session, I will mostly show you examples and exercises. Everything I will tell you is also on the slide set you got in your email. So feel free to look at it later, so you don't need to take extensive notes. So the first part, we will go to aflow.org. We already saw the start page a few times already today, but this time we will go in a little different part. So in general, in the top of the AFLOW page, you see this AFLOW schools and seminars. Whenever you have time or you're interested in learn more about AFLOW, click there. Every 2 weeks, we have very great seminars from excellent speakers from around the world. So if you're interested in material science, always an interesting hour. But also past schools are archived there, and also this will be archived there. So if you to revisit something, go there, it will be always helpful. And also on here, you see always like how many materials we have at the moment and how many properties. And this goes up with time. In the next section, you see a little overview about what kind of information we have. As some of the properties are way more intensive calculation-wise, we don't have as many. For other properties, we have them nearly for every structure. They're kind of a basic property that we calculate for all of them. But this shows you a little bit that this is not a constant thing. It really depends a little bit on the structure. If you scroll down a little bit, we are going to the apps and documents part. Today, we already saw the prototype encyclopedia and the machine learning. And now we will look at the search function. So if you click here, you come to our detailed search page. And there we have a few important parts that I want to show you. First of all, this part in the middle, this helps you if you want to select a complete group of materials easily and quickly. Okay. Then next to it, we have logical operators. So if you want to do carbon, hydrogen, you can use this button to get the right connector. So these are really, really helpful, so you don't have to remember all of these. The next part is here in gray, a tool you will use nearly every time. It says how many species or how many different elements you want to have in your search results. This helps you to limit your search quite effectively. Let's select some simple systems. Let's take sodium chloride, for example, and we want just systems that actually have both of them in them. So the number of species is 2. Now, the nice thing about the search is it's not just limited to finding a specific species, but you can also look at different properties. So up here, you have the little slider that gets you from the periodic table to the property filter. You can also use this little switch here if you want to see both of them at the same time, or want to use a slider, as you like. Slider is a little bit easier if you have a compact system. On the left side here, you have most of the properties we actually have available, and you can add them to your search. So one very common one is here. And on the right side, you see all the information you will get directly with your search. See, we now have the electronic band gap at this part. And here you have some extra information like, oh, do you want to see this column in the end? Or do you want to restrict the value? So it could be that you just want systems with a band gap of at least 3. right? So you can add this value in here. And mostly if you want to limit your search, but you're not interested in the particular value of something. When we set this all up, we can just hit our search button. And you already see we give you a hint for later how you could do this search using an API. But for now, we see here now our results. You see these numbers or the AFLOW ID. This is how we uniquely identify structures. So even if you have multiple results, they are all individually identifiable by this number. And then in the table, you see the different space group, the person symbol. So that's something you heard from before, right? This is our symmetry information. And then we have the band gap that we added in here. You also have the little sorting arrows you can use here to get just the structure you want. Most of the time when you use the web search, you want one particular structure. So you just click on it and you come to the result page that you also saw before, right? So you have, again, information on how this structure is built up. You can all use this like structure and symmetry thing to get a better idea of how the structure looks. And then when you scroll down, all the information we have on the structure is presented in we sorted for the band gap. You see here the plot of the band gap. We're missing at the moment the one on top. As you saw in the search, we have more than 5, so we have to to scroll a little bit down, and then we actually see nicely our band gap for this substance. So see this tool on the website really as a quick way a substance. As AFLOW has such a big collection, most of your common metals, alloys, and a lot of ceramics will be in there, and you can get a very quick idea about a certain substance. If you want to look at a lot of them, of course, this will be quite slow, and it's also not really feasible to do deeper analytics. Want to dig a little bit deeper and you found a specific substance that is interesting to you, we also give you the downloadable files here. Mostly the structure can be very interesting for you if you want to visualize it in other softwares like VMD, for example, or if you want all the raw data, again, you can use this AFLOW JSON or AFLOW out and processes in different languages. Right. So if you really have to or want to collect specific structures that you searched and looked at. So this is your way to get all the data quickly for a single structure. Any general questions? I think this is kind of self-explanatory, actually. So I would go on to a little bit more interesting part, where we can use an API to actually information in a more efficient way. Okay. So again, all these informations are in the slides, so you can use them if you forget a little detail. But now let's go to the search API. So the basic idea here is all the functionality you have on you should be able to leverage the API to get the same results also in bulk. Okay. And how we're doing this is you more or less just call a website, a web page that's constructed like shown here. So you ask a certain server. So this is our AFLOW API server. And then what we call a matchbook, all the arguments to your search, like what species do you want, what properties you're interested in. And all of these are put together in the matchbook. You can follow this link if you want to see all the properties. So there are quite a lot. we will just cover a few examples, and I will show you later a little bit more how you can get help or how you find out what units, for example, some of these properties have. And then we have a second part that's called, what we calling directives. This is more to tell the server, how do you want your data? Most of the time, you probably want just as a JSON, because most programming language give you a nice tool to work with this data. But you can also get it as an HTML formatted, or you can also say how many entries you want to receive, and go through different pages. But as this is kind of a bit try, if I just go through all the things without doing, I will again show you a little bit more about this now. Okay. Switch back to the browser. So if you want, you can kind of click along with me. Again, all these Binder documents are available to you directly in Binder, so you can click it, but also on our GitHub page, if you just want to look at it or try it out on your own computer later on. And in the top of the notebook, you also have a little collection.
Screen. I don't know if you have it up.
Oh, sorry. Let me switch the share again. Maybe I didn't click the okay, better. Sorry. So as I said, in the top of the notebooks, you will have a short summary, so you don't need to start cold if you want to look at it again. But let's have a little look. So this is just a helper function to make it easier for us to look at the JSON, the server response. And let's dig into it. So first of all, we have different helper functions that gives us information about the API. So if you just call the API, that's not very nice. Okay. It was just a cold start. Okay, you just call the API, which is just the question mark. It gives you more a general help. So if you forgot how to use it, just use a question mark and it will tell you all the important part and tell you what references you can or should use if you use this data later on. If you want a bit more specific informations, you can ask for the schema. And then you get back all the different information we have on what is the description, for example, what type it is, what are the units. So this is the very, very detailed information. So you before today we had the question, oh, what is the unit of something? These are all listed in here. So this is really your prime resource if you need an information. I will show you later a little better way if you want just the information of a specific one. There's kind of a shortcut for that. Next thing is, as you saw in the general search, we have different operators. We can add things together. We can say or not. So that one of the easiest questions you could ask, okay, I want everything that has chromium and 3 different elements in it. You also see this catalog one. This just limits to ICSD data. This helps you to get a little bit more experimental relevant data. So it's kind of a filter that limits the number of results you will get. If we run this, you now see we get this paging. So overall, we have 862 results, but we now just got a first tranche of it. And then we can look at them. So it tells you what is the component, compound, what is the AUID. Again, this is the unique identifier to find this material later again. And you get some standard information we always include, like what is the space group, the symbols, and of course, like a list, what species is in it. Not super helpful yet, but what is important, all of them have like 3 elements and one of them is always Chrome. So like our search set. In the next example, we now want everything but without oxygen. So this not operate and if you look up here, none of them will have oxygen. I mean, also a little bit unlikely that we just get the right one, but you can trust me, this filters out all oxygen of our search results.
Hey, I think it would be, we might lose you at some points. Do you mind turning off the camera so we increase the bandwidth?
Sure.
Yeah.
Hope this helps.
Yeah, it will. Thank you.
Okay, so then just shortly again, exclamation mark gets rid of something. So exclamation mark O says no oxygen for our search. The next one can be very helpful if you try to build structures together, is the OR. So this will get either chromium or mangan in our results, still with at least 3 systems. So here we have one that has chromium, and maybe one of the later one will have, okay, probably all the first ones are chromium, and but what you see, we now get over 2,300 results. So the mangan one are probably in the later pages of the results. And last for our combining together results is now we want them to have chrome and selenium or tellurium. So now we connect the and the or. And if you now look here, we have chrome SE, right? And we will have always either selenium or tellurium. And you see again, the result number is shrink quite a bit. Do we have an example with, let me look at page 2 for you. Yeah, example. So we have chrome and selenium. So with these operators, you can build nearly every search you want for different species. Again, you don't have to remember everything right now. If you come to the point where you want to create your own searches, go back to this notebook, look at the examples, and try to look at it a little bit more. For now, all our results are a little bit limited because we don't really see any new results, right? We just had like the space group. Now we go a little bit more interesting and say, okay, we want EGAP to know. But you see for this result, for example, there's an EGAP null. So for not for all structures, this value is actually calculated. So what it gives us back is simply every entry that has 4 elements in this. So you see it's nearly 500,000. But we actually just want the one that have an EGAP. So what you can do is you can use the little star symbol to tell the server, I just want entries that actually have the value I'm searching for. And now instead of 500,000, we really just get the ones that have actually a value for EGAP. Of course, it can be it can be 0, but we will not have empty entries anymore in this set. So this is kind of helpful. And then, as in the search, we can limit the results. So if we put a number and then the star, this means everything that is larger than this value. So if we now look at gaps that are at least 1, but you also can limit it on the other side. So now we have between 1 and 3. So we will have no EGAP that is actually larger than 3. Let me just reverse this quickly. And come on, okay. So we see now the largest EGAP we have is just 2.998. So we limited our result, and you also see it just 3,000 results. Next, very very useful part is, you see, I'm manipulating this paging directive sometimes. This helps us to serve the data a little bit more consistent to you. And especially if you try things out in a browser, it protects it from being overwhelmed. We saw some of the researches we did before would return 500,000 entries. This is something you don't want to download in one go. So this paging helps you to avoid this big of a data input at once. And you see, as we now go from page 5, we don't start at 1 anymore, but we start somewhere in between. So this is helpful to navigate to a certain page, and you see there's still the same information inside. You can also, so normally the default is 64 entries per page, but you also can set a certain number. So if you know you need to download quite a big chunk of data, you maybe want to put this to 100 or 1,000 and then do the pages this way. So in this case, this will now go from 501 to 600, oh, 401, sorry, we start, of course, at 0. So 501 to 500. So you can tell the server quite precise how you want your results presented. Another very important part of this sorting of paging is it also is responsible for how you want to your data be sorted. So if you just use the normal paging, the data is sorted after the first entry, but in the ascending order. And if you put a minus here, it is sorted descending. So you remember we did this earlier a little bit. Here we will have first the biggest EGAP of 2.8. And when we go down more, we see it shrinks to 2.96 and not 99 anymore. So this is a very powerful tool for you if you want to search for a specific entry of the largest of a certain set, for example. And then a very cool feature is also, as you saw in the general search bar, a search page, that you could have different groups. For example, if you want to know everything about all the metals or compare all the metals, you would need to type out all the metals with a column in between, and it would be a really, really long search. And to keep you safe from this, you can use the same names you see on the general search page here. So for example, you can just type metals in the species selector, and it will limit it for you automatically. So this is very, very helpful to make more compact searches for you. Okay. So you see now here, these are just comprised of a metal and a carcinogen. So for example, beryllium and tellurium. So this helps you to create complex searches quickly. Let's do a bit more complex example where we actually use these things together. This, as you saw before, we have little Python example codes that makes your life easier. Feel free to use them in your own codes, expand them. In general, we don't really try to provide like a big library that does all or abstract this all away, because we think it's very useful for you to know the underlying information. So if you maybe change from one language to another, you can still utilize the AFLUX data. So Python here is really just a little example, right? We, for example, use C++ to query our own data. So we think it's very important to stay flexible, and whatever comes maybe after Python, you should still be able to use our tools. So this whole helper block gives you two functions. One is AFLUX help. This uses the API and the help keyword to give us a little information about things we're looking at. For example, here the bulk modulus. Okay, we see okay, returns a modulus calculated using the Voigt-Rose-Hill average by AEL, and we see the unit is in GPAs. So what we now can do is we can use the second function that is called AFLUX request. That just matchbook, so the part that actually describes what you're interested in. And we have here the page information. So we want the first page, but sorted in a way that we have the large value first. And what we try to do is we try to find the bulk modulus that contains Titan. Again, we use the ICSD database because they are more experimental linked structures. And we want to find out if it's a metal or an insulator. So we collect or we request all this data from AFLOW, and we have it now in this AFLOW request. And because we already sorted, we can just say the first, so in Python terms, this is 0, the first entry in our results, and we want to know the type of band gap. We want to know which compound we actually have and what IOID it has, to show the highest bulk modulus for us, and how big it actually is. And then in the end also shows what is the lattice type and the space group. So, and now we can answer this question very easy. So it's iridium titan, and it has, has a bulk modulus of 289 gigapascal, and is a cubic lattices type, and has the space group 221. So this more or less gives you a way to quickly get information again about more single structure, and you can now also start to investigate the database, for example, materials you're not allowed to use in your application, for example. So you could say, I don't want these, and these. Let's do a few more exercises that are a little bit more hands-on. You see here we have 2. The solved one is already filled out. So if you want to look at it later, can use this one. For now, we use the kind of empty one, and I will go through together with you through all this data. I know not all of you probably did programming yet, so don't be afraid. We will do more or less a code along if you want. So first of all, we want to know information about the E gap and the energy cell parameters. And what we can do is we can use the AFLUX help function. So we want information about E gap, and we want information about the energy per cell. And we see, okay, the E gap will be an electron volt, and the ab initio energy per cell will be an EV per cell. So this is very helpful if you want to show the data later on. Always check your units. And now we need to construct our search term. So we want to know the E gap and the energy cells for all the entries in the ICSD collection. So first of all, we have to say, okay, we want a certain catalog. Take here the ICSD again. Sorry. Lowercase ICSD. And we want to know about the E gap of the system and the energy per cell. And then normally we put here a page, right, like the first or the third page. But in this case, we actually want all entries at once, because Python actually can handle this part quite well. So if we request this, you see we got our informations, and one of the nice things is because all the data we are giving you is in JSON, you can also easily save them locally. So you don't always have to ask AFLUX again if you work on the same system. So what you can do is you can just use the built-in tools in JSON to write the data out again. So the just write text and the JSON dump string. And then you have in your file system the new AFLUX save file that has all the information stored. And if you come back later, you can just use this line to load all this data back in. So this is nice if you, I don't know, if you're sitting on a plane or train ride and want to work a little bit on some data, save it beforehand, and then you can work offline with it quite easily. If we now want to visualize it, we can just use matplotlib, for example. And now we have to fill an array with all our EGAP values, right? So that we can plot it. And there is a very helpful trick to build something like this in Python. We can just say for each entry, in our data, we want the EGAP information, right? You see here, up here, that EGAP. And then we just want to plot it. Okay. Okay. So what you see here is now here complains that some of them are non-types. And the reason for this is that in our request, we just said EGAP, okay? So we get some values that are actually not a number necessarily. What we can do is we can just limit this to a data range that is easy for us to plot in the end. So now we do the request again, we limit our search. You could also do just the star, but then you can also all the 0 values. And if you plot this now, sorry, did I do?
Hagen, perhaps you should go to the worked out examples like.
Sorry, no, it's just, I did the star on the wrong side. Okay. And now you see the nice distribution of all the, and we can also quickly, I mean, yeah, we can just change here for the time's sake. We can also do the same for the energy cell that we collected before, right? So we have the energy cell per EV. We say see the structure, how the data is distributed is quite different. Of course, often when you try to get data, you will need to modify it a little bit. Sometimes you need to combine different results to get a new value that is more helpful for you. One example is, for example, the stress tensor. The stress tensor is not a single value, right? So to plot it here, we would need to figure out the magnitude of the stress tensor, so either in the max or the min part, and then put it together in our collection. If we plot this, we get this really nice histogram. What does it show us? This shows all the entries in our AFLUX collection or in the ICSD collection actually relaxed quite well. So this stress describes how much force is still in a cell after we relax our structures, and you see we don't really get over 10 kb, mostly because AFLUX of course checks for this, and it would it be larger, it does another relaxation. But this is a nice way, for example, for us to check that all our code is still working as intended. So thank you everyone for your attention. I will give you over to Simon for the next topic. Again, if you want to play around a little bit with the API, feel free to use the notebooks and change some parts as you wish and just play around with it. Any questions? Okay, then Simon, please.